Hey everybody, and welcome back to Linear Algebra Online. So this is the first video in a series of review videos, and the problems I'm going to be putting in these review videos really cover everything from the whole year, but I'm trying to highlight what I think of as some of the most important stuff that you definitely want to know. So this first problem just says find all the eigenvalues and corresponding eigenvectors for the matrix. In addition, state the algebraic and geometric multiplicities of each eigenvalue and state whether or not the matrix is diagonalizable. And so this is just lots of different stuff in here, but all really, really important stuff for our course. So you definitely want to make sure that you know how to answer a question like this. Super important thing for a final exam, like in prep for a final exam for linear algebra. So to start off, you definitely just start off by finding this characteristic polynomial, which is going to be the determinant of this matrix, right? So we got 2 minus lambda, negative 5 minus lambda, 3 minus lambda. We got a 0, a 2, and a 0, a 0, 0, and a negative 3. And so then we got to compute our determinant here. And so we'll do determinant of a minus lambda I. And fairly nice determinant because there's a lot of, zeros in here. And, one of the things that we learned is you can do determinants along really any row or any column. And so what I would definitely do is I would either go along this column or this row. So let's just think about it along this column, or row, I guess. And the only thing you got to be careful about is like the signs, how you do that with the signs. So if we were going to do it along this row, we would have 3 minus lambda and then times by the determinant of this, and it would be positive. So, basically you're just going to get 2 minus lambda times negative 5 minus lambda, and then minus these multiply together, so really plus 6. If you do that out, and you just solve for lambda on that, it's a fairly nice one actually. It can factor really nicely. You get lambda equals 3, negative 4, or 1. And so those are your eigenvalues, right? That's basically the method we use every single time for the eigenvalues. Then for eigenspaces, you just plug in, each of these values and you reduce the matrix down. So if I do a minus 3 lambda, or 3i, right, I'll have negative 1, minus 3, 0, 2, negative 5, plus 3 is negative 2, 0, 0, 0. And then that will be 0. And so then you can just do, RREF, and you'll get, for this one, you get this matrix. And I actually sort of forgot it over here. Of course, we're augmenting this with the 0 vector because we're sort of, we want to see where we're sending this into the null space, right? And so this is the matrix you get, and this one basically just says that, x1 here has to be 0, x2 has to be 0, but x3 is free. It can be anything, and so we would just do, kind of like think about parameterizing it and saying like x3 is equal to like t, and so the eigenspace for this eigenvalue of 3 would just be the span of like any vector like 0, 0, 1, like anything in that span. And what this means again, right, is that anything here after the transformation, after this matrix is applied, anything in line with that vector just stays in line with that vector. And the eigenvalues are the amounts by which things get scaled. So, you see a negative, that means that things get flipped. But then, a negative 4 means it gets flipped and stretched by a factor of 4. So this would mean that, it just doesn't even change. It basically stays the same. We saw that with when you get eigenvalues of 1, that's like we saw that in our orthogonality unit, and that really just means that things stay the same size, or length really is a better word there. And so you just kind of keep doing this process. If you do that for the other ones, you're going to get that the eigenspace for 1 is the span of 3, 1, 0, and then the eigenspace for 4, for negative 4, sorry, is the span of 1, half, 1, and 0. And it's the exact same calculation. You just plug in 1 for lambdas and do REF and all that stuff. So then turn to this question about diagonalization. So a very, very, very important result from linear algebra is just this idea between the algebraic and geometric multiplicities, okay? So the algebraic multiplicity is 3, because there's 3 distinct eigenvalues. That has an algebraic multiplicity of 3. Then geometric multiplicity is the dimension of the eigenspaces. And so you've got these 3 different eigenspaces. And so since those are the same, I said that a little funny. Since this, let's take, it's independent of the eigenvalues, is what I really want to say. So there are 3 different eigenvalues there, but each one, sorry, this is kind of written wrong too, has algebraic multiplicity 1. And each corresponding eigenspace has geometric multiplicity 1. So you can just say, like, note each corresponding geometric multiplicity is 1. And so since those two are equal, then you're going to be able to diagonalize it. That's the reason why you can diagonalize this matrix. And to do it, right, what we basically just need to do is come up with that matrix P. So P is just going to be the vectors, the eigenvectors will just go in as the column. So we'll have 3, 1, 0, 1 half, 1, 0, 0, 0, 1. And then you can get like P inverse from that. There's going to exist some P inverse. And, the reason that things are not diagonalizable is, honestly, I always call it, just teach it as like it's a space issue. If you had an algebraic multiplicity for 3 of 2 instead of 1, then you have this, where's 3? 3 is over here. Then you have this geometric multiplicity still. You basically wouldn't be able to fill up the matrix with the right amount of vectors. You would need, if this was 2, had algebraic multiplicity 2, you need 2 columns to be filled, and so you would need a dimension 2 eigenspace there. But, here everything's good because every single eigen value is going to give you a vector that you can put in, and then you're going to be able to invert and be able to do the whole, matrix computation to diagonalize it. And when you do at the multiplication, the diagonalizing, right, you would get these on the diagonal. That would be your diagonal matrix. So a lot of really important stuff there from our eigenvalue, eigenvector unit, kind of all summed up in one problem there. All right. Another thing that I just wanted to take time to talk about, if we're starting this review video series, is a really important theorem from linear algebra, the fundamental theorem of invertible matrices. So the book has multiple versions of these, and this is what they call the final version. And I actually cut off a few. There's a whole bunch of things here. And I actually cut off a few because we didn't learn the last little bit of this theorem. But the fundamental theorem of invertible matrices is insanely important, which is why they call it fundamental. And what I really want you to know is that you should be able to read down this list and see that really these are all equivalent statements. So that's what this theorem is saying. It's basically has an n by n matrix, where you have some sort of transformation from V to W, like some vector spaces. It's a linear transformation. And it's just saying that if the matrix that represents that transformation A is invertible, then all these different things are also equivalent to that idea. Like take these two you learn together. Like rank of the matrix, it's basically full rank, right? Because n by n, which means that it's only going to send the zero vector to, 0. Everything else from V gets transferred over to W. A lot of these should be pretty intuitive. And a lot of them kind of are redundant. Like they're talking about the matrix A is invertible, and then they talk about the transformation is invertible. Here they're talking about the kernel of the transformation being the zero vector. That's basically like saying the nullity of the matrix is equal to 0. So, these matrices are just representations of linear transformations. So lots of really important stuff. I would just basically suggest that you read through these and make sure that when you look through them, there's nothing that seems out of place and weird. These are all equivalent ways to say the same thing. If we had more time in this course, one thing that I would have done is I would have had all of you go through and prove different if-then statements here, basically. So, if you assume this, you should be able to show this. And then if we have this, you can show this. This statement should imply this one. And if you do that chain all the way through these statements and then go from here and prove it implies this, then that's like the way we've shown that these things are all equivalent. It basically creates like an if and only if statement because you kind of create that back and forth loop. And so those statements are honestly kind of like the building blocks of so much stuff that we even do. So make sure that you understand this theorem and what these different parts of this theorem are saying. All right. You definitely want to just know how to do like basic matrix computation kind of proofs. So I'm going to just do an example of what I mean by that. So if A and B are invertible, I want to prove that AB is invertible and that AB inverse is B inverse A inverse. I picked this one out because it shows an important, this is that like socks and shoes kind of thing. Socks and shoes. And there's, a lot of socks and shoes kind of things like that. In linear algebra, we see it with the transpose also. But these are the kind of proofs that I definitely, feel very comfortable giving you on a final exam, and you should feel like you can do these things. If we want to show, I'll just write this out. So to show AB is invertible, we show ABX equals I for some x. And that x will be AB inverse, okay? And so to do this, we just kind of, all we have is, these two statements. All we have are these two statements, and so we're just going to use each of those. So since A is invertible, there exists A inverse. That's what that means. So we could do A inverse AB x, which is going to equal equals A inverse I. Okay, so just taking this, right, and just multiplying on the left by A inverse. And, that's going to basically imply that BX equals A inverse, right? And then you can do a similar thing. Since B is invertible, there exists B inverse. So now this B x equals A inverse thing, I'm just going to multiply by, B inverse on both sides is going to imply that x equals B inverse A inverse. And so, this does it. This shows X is a thing, and AB's inverse is that B inverse A inverse that equals X, okay? So that's kind of how you show, AB is invertible. You just showed the existence of X, and then to show that AB's inverse is B inverse A inverse, you just go through that computation and solve for X, literally, right? So that's kind of a important type of proof that you could run into, and also important result if you think about it. If you have two invertible matrices, its product should be invertible, and this would extend really nicely. The proof of doing this in higher multiplications is fairly straightforward. All right. Don't think I ever proved this result when we were talking about determinants. I just kind of gave it as a property that we could use, but I just want to prove it here. So I want to prove that k, where it's a scalar, times a is k to the n determinant of a. And to do this, I'm basically going to use a property of the determinant. We know determinant of ka would just equal determinant of k times the identity times a, right? It's basically introducing the identity. It's not going to change anything there. And then you can use this fact that the determinant of a product is the product of the determinants. And so I can write that, okay? And what I want to show is, the following. I'm going to prove, as like a mini problem, that the determinant of ki, I'm going to put a little n in there, is k to the n, like for all n greater than or equal to 1, okay? And to do this, I'm just going to go through an induction problem, which is good practice to see. So the base case is pretty straightforward. So for the base case, let n equal 1. So we literally just have the determinant of k, which is going to equal k. Basically it's just literally a 1 by 1 matrix k, and trivially that determinant is k. So good, we're done with that one. Now I'm going to assume that the determinant of ki, I'm ready to use an n, so I'm going to go with something else or I'm already using k, sorry, so I'm going to go with something else, because a lot of times here we assume k and we show k plus 1, but I'm going to assume m and show m plus 1. So I'm going to assume the determinant of k times I sub m is k to the m, and show that the determinant of ki m plus 1 is k to the m plus 1, okay? And so to do this, okay, I am going to create a block matrix, which is good review here. Maybe I'll do it like this. So ki m plus 1 equals this matrix, where I have a k up there, and then this is like a block matrix with a 0 and a 0, right? And then down here is just KIM, right? And so the determinant of KIM plus 1 is just going to equal, right? If you literally just do the determinant, it's like you blank this out, you do K. These are 0 matrices, right? You do K times the determinant of the part down here. And really these are, I guess, 0 vectors. I should probably be a little more clear. That's like 0 vector transpose. And that's truly just the 0 vector, which you can think of as a matrix too. But so this is determinant of k times I m plus 1 is going to equal k times the determinant of KIM, which is k times, this is where I'm using my assumption. It's going to be k to the m, that uses the inductive hypothesis, which is k plus 1. And since, I showed that here the m plus 1 case implies m plus 1, and the base case holds, then this should hold for all n. So this proves determinant of kin equals k to the n. Right? That does like my mini little induction proof. Now to go back to the main problem up here, I'm basically just going to utilize a fact about the determinant of a matrix. So, since this is just a result that we can use here, determinant of A is the product of its eigenvalues. Yeah, never mind. I don't actually have to do that here. So it's even easier than that, because all I wanted to really show was that determinant of A is just pops out. I mean, it already is there, right? I've used the property to pull it out. So I don't actually need to get in. There's an argument you can do with the eigenvalues that I was about to get into, but you don't need to worry about that. So so this proves it, literally, right? Because then determinant of Ka is just going to equal determinant of Ki n determinant of A, which is equal to, based on my little mini proof with the induction problem there, I have K to the n determinant of A, which does it for me. So that's kind of how I would go about proving this result. Conceptually, what you want to think about determinants is, they are a measurement of like the scale factor change in the transformation. And so if you multiply the matrix by K, right, it basically scales the determinant by K to whatever the size of that matrix was. It is not just going to be able to be pulled out because you're doing it in multiple dimensions. And so, you get determinant of Ka equals K to the n determinant of A. So I think that's where I'm going to end this review video, and we will pick up some more problems in the next one.